Okay, welcome to the second homework video for Chapter 2. So in this video, I'm going to do I'm going to do problem 29 from page 75. So in this problem, what we're trying to do is maximize the production of component 1 and component 2 so that we can produce our ignition switch. And these components can be built at our Buffalo plant and our Dayton plant. So component 1, component 2, component 1, component 2. Now per the problem, the Buffalo plant can produce 2,000 units of component 1 and 1,000 units of component 2. And then in the Dayton plant, at max, can produce 600 units of 1 and 1,400 of 2. Now, probably the most important sentence in this entire problem is when they say, look, the Buffalo plant can produce 2,000 units of component 1, 1,000 units of component 2, or any combination of the two components each day. So, for instance, 60% of Buffalo's production time could be used to produce component 1, and 40% of Buffalo's production time, therefore, could be used to produce component 2. All right? So what this means is as follows. So if you think about what's component 1, the production of component 1. Well, that is equal to 2,000 times the proportion of time the Buffalo plant is producing component 1. So in other words, if B equals 1, right, therefore I'm going to produce nothing but component 1, I could produce 2,000 units, plus 600 times D, where D is the proportion of time I am producing component 1 in the Dayton plant. Right? And then conversely, component 2, well, this is going to be equal to 1,000 times 1 minus B, right? And your book gives you that example. If 60% of the Buffalo time is spent producing component 1, then 40% is used to produce component 2. And then similarly, we have 1,400 times 1 minus D. All right? Now the key, at least in my opinion, to understanding this problem is to think as follows. We already know that we have to produce the same number of each component, right? Because your problem says the component, no, it's right here. Yeah, each ignition system is assembled from 2 components. So in other words, to get one ignition system, I need to produce component 1 and component 2. Well, that also tells us then that the production of component 1 must equal the production of component 2, right? Because you don't want more units of component 1, because then you're going to have excess units of component 1. There's going to be left over, right? Because for each ignition switch, I need 1 component 1 and 1 component 2. All right? Well, hopefully this is starting to get you to think, hey, wait a minute. What I should do is maximize the production of component 1 subject to the fact that the amount of component 1 must equal the amount of component 2, right? That's the way I thought of this problem. So then I just set these equations equal to each other. So I just had 2,000B plus 600D was equal to 1,000 1 minus B plus 1,400 1 minus D. And then I'm just going to solve this. So 2,000B plus 600D is equal to 1,000 minus 1,000b plus 1,400 minus 1,400d. All right? And so I'm going to move the b's and the d's over. So this gives me, I'll write it down here, 3,000b plus 2,000d, right? And then I'm left with equals 2,400. So there's my constraint, right? And this constraint simply says, look, I have to produce the same number of units of component 1 as I do for component 2, right? And presto, you're done. Well, almost. I'm sorry. That was bad. Almost done. Because I hope you would realize that I still have two more constraints. I have to put a constraint on B and D because they both have to be less than 1, right? The amount of time, because remember, B is the proportion of time that Buffalo spends on component 1. Well, the most that can be is 1, right? The least that can be is 0. And then same with Dayton, all right? So you formulated this problem to something like this. I want to maximize I want to maximize this, 2,000B plus 600D, 2,000B plus 600D, subject to my, to that constraint, 3,000B plus 2,000D is equal to 2,400. And then, of course, I have B less than or equal to 1, D less than or equal to 1, and then I have my non-negativity constraints where B, comma, D has to be greater than or equal to 0. So there is my problem. So setting this up, I'm going to find B and D. And I got my parameters, my choice variables, my objective function, fine. And what do I got here? So my parameters, 2,600. Placeholders, 1, 1. Objective function is always a sum product of choice variables. And, darn it, I screwed that up. I like to go in order. Sorry about that. So, sum product of parameters and then choice variables. All right? And then I've got my constraints. I've got 3 of them. So constraint 1, 3,000, 2,000. Constraint 2, 1, 0. Constraint 3, 0, 1. Leave these open. So this was equal to, less than or equal to, less than or equal to. Make that a little smaller. This one, 2,400. Okay, so 2,400, 1, and 1. Let's make that a little bit smaller. And then, of course, here, how much of my constraints am I using based on my choice variables? So, another sum product function. So, choice variables, parameters, hit OK. And then let me anchor the choice variables. I'm going to copy that down. Okay. Let me make this a little bit smaller, smaller, smaller. See if I can get everything on. Good. I got everything on one page. Okay. Well, there. We are done. We are now ready to solve this problem. So, data. Oh, solver. Sorry about that. I had these 3 highlighted. Solver doesn't like it when you have multiple cells highlighted. So before you open up Solver, just, put your cursor in one cell. So Solver, Objective cell must be a single cell. I know. I don't know what. Okay, I don't know what's doing now. So set the objective, 2600. I'm going to maximize that by changing these two cells. And I'm going to delete these crazy constraints that Excel put in there. All right, and then I'll put in my own constraints. So this number equal to this number. And then these two constraints have to be less than or equal to these two. And we'll hit OK. I got this box checked, Simplex LP, I am ready to go. So I hit OK. Okay, so what is this telling me? Now remember, I was maximizing the number of component 1 pieces that I should produce. So this is telling me that I should produce 1,600 units of component 1. To do that, I'm going to use 80% of the Buffalo plant to produce component 1 and 0% of the Dayton plant to produce component 1. So remember, for component 1, here, let me go back up and show you. Right, so for component 1, it was 2,000 times B, right, plus 600 times D. Well, D is 0 in this case, so take the 0.8 times 2,000, right, and that's the 1,600, okay? Now, how much of component 2? Well, component 2, I'm going to take 1 minus B times 1,000, 1 minus D times 1,400. So for component 2, I am going to take the 0.2 times the 1,000, right? That's what I just showed you, 1,000, right? The 0.2 is 1 minus 0.8 times 1,000. And then, of course, D is 0, so this is just the 1,400, right? The Dayton plant is going to be used exclusively to produce component 2, so this is just plus 1,400. And let me scroll out. There we go. And put parentheses around this. There you go. So we're going to produce 1,600 units of component 2. And by putting, you didn't need to go through all this. I simply wanted to show you, hey, we did it right. You know what I mean? We're producing the same amount of both components. Okay? So there you go. There is problem 29 from page 75. I will see you later.